for coming today. Yeah, I'm Spencer at Meibel, principal scientist. So today I want to talk about running AI at scale. So we're not talking about humans running similar queries over and over again manually. At Meibel, we're thinking about how engineering teams use generative AI to build products and build a platform to help reduce those teams' pain points that they have when they're including generative AI in their pipelines. So with that perspective, I'd like to cover some of the considerations that address some of those pain points around properly processing and retrieving data in AI pipelines. So this is our roadmap for the next 15 or 20 minutes. Most of us are probably familiar with basic concepts like RAG, Retrieval Augmented Generation. That's using similarity metrics to retrieve relevant documents for your given query to improve the results of that query. I want to speak a bit more generally about augmented generation systems, not just using similarity embeddings. There are three main components of an augmented generation system. There's the ingest, the storage, and the retrieval. I'll be discussing the concepts of structured and unstructured data and how they address qualitative or quantitative questions, because among other things, whether the question is qualitative or quantitative makes a big difference between the suitability of the data to the question. So the first two components, ingest and storage, are relatively intertwined. So I'll overlap those two for the first half of the talk, and then retrieval will follow with an eye towards ensuring we are matching our data to our questions. So it's complicated. Legal documents, web pages, financial documents, internal corporate documents, academic papers, databases, novels, product specification sheets, FAQs. What are the different ways of ingesting these documents? How do we ingest different types of documents so that retrieval is effective at scale in your pipeline? People generally think of structured, semi-structured data and unstructured data generally. Let's start with unstructured data. So as is typical, we can RAG it, right? Let's just take the text, embed it, put it in a RAG, and now we've got embeddings. Maybe we do overlapping windows of that text, and we can throw it into a vector store for later comparison and retrieval. But do we just calculate embeddings for overlapping windows of text? So here's an example of why you might not want to do that. So this is a transcript from the BBC News. The first paragraph is about the war in Ukraine. The second paragraph is about the decline of emperor penguin populations. If you do the whole thing, your embedding will be terrible. So you might want to do it by semantics, right? The first paragraph is semantically very different from the second one. So that is one consideration you need to think about when you're creating these embeddings in the first place. Let's go to semi-structured data. So behind that human readable web page on the left there, and this is a completely random web page, by the way, the underlying raw document has JavaScript, CSS, HTML tags, and other irrelevant text that we don't care about. So we need to ensure that we're parsing this properly and extracting only the relevant pieces, which will likely look a lot like the relatively simple human readable view that we see on the left side, as opposed to the right side there, which is a mess of things we don't care about. Let's talk code. So how do we parse semi-structured data with code? So underneath the veneer of maybe a lack of structure, code is of course highly structured, right? There are formal grammars and can be composed into abstract syntax trees that we can use to make better decisions about where we chunk or parse the document on the left for later retrieval. We don't want to interrupt a function and then somehow make assumptions about what the rest of that function does. It's good to see the whole unit of code for similarity checking. So unstructured data parsing isn't trivial. Semi-structured data parsing isn't trivial. Surely already formatted structured data doesn't need a lot of work, right? Well, when we say structured, we mean organized in this case. So the data has a well-known schema. It's got columns you can refer to and they're machine readable. So while the structured data could have discrete or continuous data, you might be good to go. But there's a big asterisk, because structured data doesn't mean that all the fields are discrete, continuous, or even ordinal. So we might be right back to our NLP problem to begin with. That field needs an LLM, I guess, right? Generally, if you have natural language in a database, those documents don't necessarily warrant their own RAG, just the cases we've seen. But we can at least, so if we're not going to put those fields into a RAG, which we could do, we can at least augment them using sentiment analysis or topic modeling. So now we have ordinal or classification features for later retrieval. I'll talk about how to retrieve those later. But I want to revisit unstructured and semi-structured data and talk about another category, that is structurable data. So we're just going to define it this way. So structurable data is unstructured data from which a structured extraction can be derived. And it'll be easier to understand this definition with an example or two or three. So let's take one of the most unstructured examples there is, a fiction novel. We can most certainly calculate all the embeddings as we've done before, right? We have our RAG system, bing, bang, boom, but we could also extract structure through a list of character relationships in that novel. So using that list, we can create a graph. And now we have a graph database, let's say. So we can take unstructured data, extract character to character relationship structure from that, and now put all the data in a graph. So that's sort of how, hopefully that follows the definition, right? So unstructured data, but we extracted structure from it. So here's another example. This is a product specification sheet. There are lots of instructions, guidelines, prohibitions, warnings, parameters, and specifications for this particular lantern, or do you say torch here, or is that just flashlights? So let's recognize that there's a lot of text, some tables, some image annotations. Not only can we extract specifications from the text or table, but we might have OCR. We might have to do OCR on some or all of this document because some of that stuff is not even text or machine readable. From that text and or OCR extraction, we can get a table of values that follows a specific schema that we want to see because maybe we have tens of thousands of other documents that are similar. And now we can insert that into a relational database. So here's another example of structurable data. So this is the Maryland legal code. A lot of us from Meibel are from Maryland in the US, so that's why we're doing this one. Within it are a lot of in-text citations and references to other sections and books of that code. That code is huge. It's 70,000 individual pages, I think. HTML pages. We can embed the text as normal. We can also do something else that really increases the recall of retrieval systems. So we can create a citation graph using the in-text citations. We go through that unstructured text, pull out all the in-text citations, and build a knowledge graph out of that, or put it in a graph database. And now when we retrieve a document based on its embeddings, based on the prompt's embeddings, not only are we retrieving the theoretically most relevant documents, but also we're filling in a lot of gaps that you would not catch if you're just doing embedding matching. Now you're following this chain of reliance on other documents that maybe don't fit the prompt, but nonetheless fills in that picture a lot more based on any question you might have had or any prompt that you might have sent to that system. Typical embedding similarity matching will miss those gaps and connecting documents. So I talked about aspects of ingest and storage. As with any machine learning pipeline, how we parse, preprocess, transform, and store the data is critical. Now we get to the whole reason we did any of that ingestion and storage work in the first place, and that's getting an LLM to produce a useful, accurate response. So the last half of this talk is about retrieval and some techniques we can use to help ensure good retrieval at scale. We have a question we're submitting to the system, and we want to know, number one, what data source or data sources are we retrieving from in the first place? And two, how the LLM might have gotten to the answer it produced. For the first point, let's refer to the pretty circle and red arrow. So whether we're answering a qualitative or quantitative question is a significant determinant for which database or schema we might want to use. There are, of course, other factors, but the questions we want to ask are always critical for determining how we process our data and how we create our pipeline in the first place. So this is an example of a qualitative question. So unless you're counting the weight activations of an LLM, if you want to be pedantic about it, the answer is not computed, but generated by the LLM. And to answer this question, LLM has to match source documents against the prompt and then synthesize a response using those documents and the prompt. There's no counting done, right? And the answer is, derived from those documents. There's no counting of those documents. This is a quantitative question. So To answer this question, you need to count the instances that match those criteria. So this requires a summary statistic. We can use an LLM for this by having LM generate a database-specific query if we have an underlying database that has this data in it, and then we can run that query against the database. And then the database is what's doing the work there. It's doing the counting. It's doing the summary statistics and calculations. So, if a regular RAG system, unless there's some up-to-date document that's always got, the latest contraband seizure numbers, we couldn't use that for this purpose. For the most part, vector stores are good for qualitative questions, given what those embeddings signify in the first place. Relational databases are good for quantitative questions, given their ability to calculate and provide summary statistics. And graph databases provide decent coverage of each kind of question you might want to ask, both qualitative and quantitative. We need to know which data source to use for which type of question, and then we need to know which database and schema we are asking when we ask the question, right? Which one we are going to be retrieving from. So let's be sure as we build a system, that we're creating the correct database and schema for the pipeline's purpose. Okay, so we've established our pre-processing and storage scheme and established the correct routes to our database and data with our pipeline. Everything's set up, we're ready to go. How do we provide some metrics for the quality of the actual responses now? So now everything's set up, we want to measure what's coming out. So people are probably aware of LLM judgments. That's things like coherence, relevance, groundedness, completeness. There are a bunch more. Those are useful, important. We use them. They do beg the question a little bit, right? Like an LLM judging its own answers, or an LLM that can hallucinate judging another LLM, right? Like there's bias in there for sure. Like I said, it does provide value. But there are additional, less well-known ways to help measure output quality. And measure output quality and hallucinations that don't rely on LLM processing. So let's go to them. One of the things that we are thinking about and do is token grounding. The user asks a question, the LLM responds, and looking at the token level, right? So the question is from the users, how water resistant is the ever ready 3324? And the answer is from the LLM is, it is rated to IPX9. Looking at the extracted data and looking at the response from the LLM, we don't see what the LLM said in the extracted data. So that makes it a little bit more likely that the LLM hallucinated somehow, right? We don't care if the LLM said the word the or is, and the word the or is not in the source. These are common words that, are part of language that you need to use. And it could just be part of the flow of the response. But less common tokens like IPX9, we care about. Second, if we've done OCR pre-processing as part of the pipeline, we can use the OCR model confidence scores as part of our final determination. Now, in this case, we're not saying the LM created a problem, right? But we're just concerned about the potential error anywhere in the whole stack, right? This is a chain of errors, and we want to figure out what the actual probability in the end is that the answer is correct. And finally, we can compare multiple LLM generations to see how semantically and logically consistent or entailed the responses are. So if we see that multiple generations agree with each other or agree with the official response, then we can either, figure out through some ensemble that this is the right answer, or that the official response has maybe some, some score associated with it, right? Probability is maybe a weird word, but maybe the probability that it's correct or not. To recap, we've gone over some of the problems involved in building these pipelines. So, with ingest, like how do we pre-process everything? It's a lot of work. There's a lot that goes into that. A lot of decisions need to be made. We've talked about some of them today. We haven't gotten to things like the metadata you might want to extract. We haven't gotten to maybe you want to do dense embeddings and sparse embeddings, right? But there's plenty that goes into that. There's the storage element, right? So we need to make decisions about which database and schema we should have for the pipeline. A lot of that we have automated out, and it's just automatically created. And then the retrieval, right? So, which database and schema do we query based on the question you have? So you can have multiple databases and schemas that have all kinds of different data, but which ones are you asking which questions? So we can do that as well. And how do you provide some more sound verification of the output beyond LLM judgments, which again, useful and good. We like them, but that, there's more that we can do than just those. So everything I've discussed today are, pieces of the platform we've built. We want to help people go from concept to production. If you want to talk about more about any of this, please feel free to swing by booth 305 or get a demo. In fact, some of the co-founders are here now if you want to talk to them. But otherwise, questions?
Thank you for the talk. A lot to unpack there. I think one of the things I'm most curious about is the graph portion you talked about there. Building an ontology, I think, is pretty challenging. It's not always research papers and books, right? I'm curious how you do that balance and trade-off between having a generalized ontology versus specific enough to answer.
Okay, so a generalized ontology. So I'm having flashbacks because this was like a previous thing. There were like sessions and meetings of people that were going to figure out what the ontology was going to be. And we ended up with, I wasn't part of it, but it was nothing, right? Like you can't do that. So if you mean like a schema that applies to a particular use case, I mean, that's I suppose like any relational database, or am I off the right track?
Let's assume that you wanted to make something for a set of books, but you didn't know which books were going to go in there, right? So having to build that.
You didn't know which books?
Yeah. Let's imagine you wanted to make a more generalized solution for fiction books or nonfiction books, right? I think that's where I struggle, which is, if I knew what the corpus was, even then probably with enough content, it'd be challenging to build the right ontology to answer questions versus the right ontology just to have a lot of coverage, right? And how you build and strategize that, I think, can be key to performance on the other end.
Yeah, I mean, we haven't really had trouble building business specific schemas and there's a question that these businesses have about their data. And sometimes it's just extracting relationships or, let's say, in-text citations or something, right? We have refused work from someone who wanted to do something crazy. And we were like, no, we can't do this, right? Like specific business use cases that, they have specific questions. It's worked out, I guess.
I mean, maybe just to follow up a bit on the specific use case, but imagine it's some university, let's say some maybe UK university or something. Sorry, and they have like a literature books for the course of something, right? Like course of English or English history or something, and potentially could be multiple books. So and the business would be, yes, we want to make sure education is advanced application for education where students could get some additional maybe materials or recommendations or questions coming based on their curriculum or something like this. And I would imagine what colleague is saying, right? Like this would be a problem, how to build ontology, let's say 5 history books, like how are we going to make sure that Henry VIII from the book is not the Henry VIII from another, country or something.
Sure. And entity resolution? I mean, that's the problem you're talking about, or?
No, like in the graph context, right? Like how to make sure that it's gonna converge, right? How to make sure it's like, I could imagine how we do NER and triplets extraction from text, from one book, from another book, how we merge them all together now. How we make sure that this is the subgraphs, because I could imagine 2 books mentioning Henry VIII. Sure.
I mean, so no businesses have wanted that. A lot of it's like product IDs, right? Like those have like very clear identification numbers or something, or references that way. We're not finding Henry VIII so far. We're finding like a serial number or something, which is got an ID. We haven't messed with like entity resolution.
Are you finding there are certain industries that are taking up your services versus other industries? I mean, we just had a good example there of, let's call it more of the academic domain compared to the product domain. So if you can talk into that, and also how do you work with domain expertise when you're building out these solutions?
First of all, yeah, we have academic circles. We're not aiming for them, and that's nothing like what we've done. Industrial companies. Yeah. So. And some significant part of it has been like these product spec sheets, right? So we are doing OCR on these things. We're identifying products and references in these sheets. Often these companies just need the generative AI piece of it, right? We've replaced pipelines for them, but they've done a lot of the work of figuring out what they need.
Yeah.
They just want the ability to, let's say, extract things from documents or something as part of their pipeline. A customer sends something in, they want to read that and then do as they've been doing, but they need that generative AI piece.
Got it.
So, we're not necessarily figuring out, and that's not our aim either, right? We're working with the engineering teams
Yep.
for them to inject the generative AI into their pipelines. We're not figuring out their business case. People aren't coming to us and being like, what can we do with generative AI? Like, well, anything. I don't know. What do you want? So they already have an established process, and we're
Great.
fitting,
So
we're slotting into
engineering
it.
teams are
Engineering
yeah.
teams. Yeah.
Well, thank you very much for your time, everyone. And please let's thank Spencer for his brilliant talk.